Okay, I'm going to go ahead and get started. Someone in the back row, tell me if you can hear me. Actually, if you're in the back row and you can't hear me, no, that doesn't make sense. Okay. All right, so I'm going to just start really briefly with a recap of yesterday's, Tuesday's lecture. Okay, so basically we did a lot of administrative stuff. You look at the slides online, that's sort of what I was reading from. And we talked about why scalability matters, okay? How to basically measure scalability using big O notation, all right? And what sort of things you need to count. So this was sort of my kind of like quick picture of why scalability matters. So here's a simple problem, and the kind of thing to take away from this is as you get more and more data, performance is improving, okay? So the really big difference is not what algorithm you use, is basically how much data you can throw at that algorithm, all right? The other thing we talked about was the cost of various operations that get used, all right? So this is sort of a bunch of the numbers that I put up there. I showed briefly this really cool little visualization. So this is basically Jeff Dean's numbers, and it's provided by the systems guy. I think he might be at Berkeley, named Colin Scott. So he put together a really beautiful visualization of this. You can sort of like look at how things change over time and so on. It used to be up on the web, but the only place I can actually find it now is GitHub, which is why I have this like this file that I showed you the other day. So if you want to like play with it yourself, you could go to GitHub and pull down that JavaScript and then and just run it on your machine. So Colin, I believe, is the one on the left. Okay, but the short story is, so computer hardware changes very quickly, but there are lots of things that don't change that quickly from a relative point of view, okay? So one reason there's a whole class on parallelizing machine learning algorithms is because our data's gotten bigger and the clock cycles haven't gotten faster. So if you want to run, on larger and larger data sets, you can't just leave it to Intel to give you faster and faster machines every year. You've got to do something to speed things up that involves using multiple processors or organize your data better. So a lot of things move pretty quickly. One thing which doesn't move very quickly is disk seek speeds. All right. This is a little bit hard to see on this resolution monitor, but if we kind of zoom in here, these are the costs of different types of computer memory. Okay. So this is a cost of a disk drive. Okay. So the cost of disk drives have been going down very fast. This is the cost of main memory. That's also been going down really fast, okay? But there is no point at which we can extrapolate where these things are really going to catch up. If you're working with big data sets, there's always going to be some data set that's so big it's going to fit on disk but not in memory, okay? So that's something that doesn't seem likely to change real soon. This yellow line in between, anyone want to guess what that might be? Does anyone have a machine in front of them that has a memory that's not a substantial amount of memory that's not like a spinning disk, but is not RAM memory? SSD? Yeah, right. So these yellow lines are basically flash memories, right? And they typically tend to be, for roughly the same price, bigger than main memory by maybe a factor of 4 or 8, okay, and smaller than disk, okay. So if you go back far enough, there wasn't that much of that. So that's why that graph only starts a few years back, okay. So these are the numbers that Jeff Dean says we should all know, and it's a little bit hard to get a kind of easy sense. If I just show you those numbers, they're just numbers. It's hard to get a sense for how different those numbers really are. Here's some visualizations. So I'm actually visualizing here the sizes of different memories in a computer system, right? So there's a hierarchy. There'll be a hard disk. Maybe that's a terabyte. There'll be main memory. That's maybe like a few gigabytes. All right. we're looking at a machine like this. Okay, and then there's various caches. There's typically one that's like around a megabyte. There'll be a bunch that are really small, like for instructions and so on. They're maybe like 4K or smaller. Okay, so just to give you an idea, the hard disk here is about 128 times. So it's 2 orders of magnitude bigger than main memory. Okay, and here we've got 16x. Here comes we've got 256x. All right, so if we're going to take something that I was about 16 times bigger than, it might be that Chihuahua. Okay, something I'm about 250 times, 6 times bigger than, it might be like a phone. Okay, so that's sort of like some of the differences. Or if we're going to do it the other way, if I'm the Chihuahua, the larger cache there is a car. Okay, or a whale. Okay. So these are big differences, okay? If you're counting how many people are going to come to your party, it's different from the number of cell phones you can fit in your party, okay? Particularly since every person is going to have a cell phone. Makes up parties really awkward. So the other thing is timing, okay? So why is it that disks behave this way? Why is it that seeks are so slow and have stayed so slow comparatively? So modern disk drives are amazing feats of engineering, okay? But you're not moving electrons around, okay? There's a platter that spins around really, really fast, okay? And what happens is that disk head is going to stay in one place, and it's going to wait for the data to spin around underneath it, okay? And if your disk drive is laid out very cleverly, so in other words, if there's been like decades of engineers working to sort of optimize how it's worked out, and if they understand how you were planning to access it, right, and their expectation is that you're going to access it sequentially, you're going to read through a file in order, then they'll lay things out so all you have to do is wait for the disk to spin to get the next thing you want, all right, and maybe moves like a little bit slowly sideways as you go from track to track, all right. But if you then suddenly say, oh, I want to get data from some totally different place on this disk drive, okay, then what has to happen is that disk head has got to move sideways, okay? So it's no longer something that's sort of spinning around as fast as you can sort of make a piece of metal spin, all right? Now you're sort of moving a physical object from place to place, all right? So it's way slower than electrons. It's way slower than moving electrons around, all right? So way slower, in this case, is like 100,000 times slower, okay? So that's a really big difference. Okay, so just again, just to kind of like calibrate this, so like in terms of time, okay. So if I want to like fly from here, let's say to LA, okay, and by some miracle I got a direct flight from Pittsburgh to LA, okay, that might take me 5 hours, okay. So if I had to wait 100,000 times longer, right, that would take me 57 years, okay. If I left before I was born, let's say shortly before I was born, I wouldn't be there yet, okay? All right. Another way of putting it, so if I could think about a distance of like 500 miles, okay, so that's the difference from here to say, I'm going to say Charlotte, North Carolina, okay? 500 miles, good long ways, all right? So that would be, instead the distance, if I could divide that by 100,000, it would be about 8 meters, okay? So maybe from like here to that camera, okay? So those are big differences, okay? Those are really big differences, okay? So Jeff Dean basically says you really should think of memory instructions as qualitatively different from disk access, okay? And you should think of seeks, okay, jumping around on disk as qualitatively different from a sequential read on the disk, okay? So everything is designed to stream through data sequentially, okay? So if you're dealing with large data, so if the data is not already in memory, okay, and you're hardly ever persistently storing it in memory. I guess you might persistently store it on an SSD, but usually that data is persistently stored on disk. Okay, if it's a large data set, it's going to be on disk. Really, the best case is to stream through it once sequentially, right? That's the fastest thing you can kind of hope to do. Okay, So Jeff Dean has said a bunch of other things. This is stuff that I pulled out from his slides. These are other things that he thought were very important. He thinks it's very important to encode your data compactly, right? Because of course, when you're streaming through that data, if you've used a very concise, compact encoding, it's going to be a lot faster than if you use a bulky one. That's actually not something we're going to talk about a whole lot in this class. It is important practically, and if you go out in industry, internships or wherever, then you'll probably learn all about working with Avro or protobufs or what have you. Okay, but we're not really going to talk about that much in this class. Question?
What does it mean by qualitatively different?
Qualitatively different means basically you're not going to use the same counters to count those things the same way, right? So when you're looking at a big O analysis of your algorithm, then you want to have sort of a separate analysis for what it's doing on disk than what it's doing in terms of its operations within memory. Okay? Then particularly qualitatively different for us means that we're going to sometimes just ignore the cost of what the computer is, the operations the computer is doing, how many multiplications it's doing, and things like that, and just focus on disk access times, right? We're organizing our computations, we'll think very much in terms of disk access. Right, so that's basically what the impact of it is now. Thank you for the question. Okay, so these are the different things to count. This is kind of our review, okay? They're sort of like these kind of different hierarchies of activities and costs of storage, okay? So that's kind of review, all right? The next thing I want to talk about is I want to spend a little bit of time talking about what kind of computations we want to do. And for machine learning programs, one very large class of computations that we think about a lot are probability computations, okay? So I'm going to talk a little bit about probabilities and scalabilities. And let's start with this problem, okay? So this problem, if you recall, what we're trying to do is we're trying to do context-sensitive spelling correction. In this example, this is one example. I want to basically distinguish whether you meant to use the word affect versus effect, given that you actually did use one of those two words. So it's basically classification. Which one of those two easily confused words did you plan to use? Did you mean to use in the context that you used the word? Okay. And I gave you guys a little demo, okay? I basically showed a program where basically what we did was we looked at finding the probability of any tuple, okay, of any 5 tuple of words, okay, appearing in some large corpus, given that the middle word was either affect or effect. So I didn't tell you where that data came from Tuesday. I'll tell you today. So it came from Google Ngrams. Okay, so that's basically all the words that appear, all the 5 grams that appeared at least 40 times in a corpus of about 1 million books, English language books. Okay, so it's about 80 billion words, okay, about 30 gigabytes compressed. If you uncompress it, it's like, a quarter terabyte or something like that. So it's a decently large corpus, okay? It's a little bit bigger than it needs to be here because each 5 gram actually has frequency distribution over years, which is how you can do these pretty plots I showed you, measuring the frequency of things like Merry Christmas over time. But once you take that corpus and you ignore the frequency distribution over years, and you just pull out the words that have the easily confusable word affect or effect in the center, then you end up with something that's quite reasonable, okay? So you can do these computations basically in brute force way pretty easily on what's left, okay? From playing with the data, we could sort of come up with some, observations about what's going on. So effect is more common. If you want to look for something that will indicate you probably should be using affect, the word not, right, is sort of a good clue. Okay. So this is, maybe if you want to sort of start out by writing some rules, that might be where you'd start, okay? But from a methodological point of view, what we did here is I built a joint distribution, okay? What I did is I built a joint distribution of these 5 values, all right? And from that joint distribution, I can answer lots and lots of questions, okay? So the joint distribution just basically tells me what's the probability of seeing any particular combination of values. And this is all, of course, conditional on being one of those kind of 2 center words, affect or effect, all right? So the recipe for building a joint distribution is really easy. I just look at every possible combination of values, all right? And I compute the probability of seeing that combination. So it's just a big table here, okay? So for the affect effect task, the data set I collected, I guess the total number of counts was something on the order of 100,000 or 100 million, right? But the actual number of values was more on the order of 100,000, okay? So it's a relatively small set that you could kind of scan through pretty easily. So we're ignoring all the things that have probability 0 that never appeared in the data, okay? So for every combination of values, we can see how probable it is, okay? That all sums up to 1. So if I want to ask any sort of question, right? So if I want to ask the question, what's the probability of seeing the word affect in the middle position, given that the word before is not and the word after is a, right? I can easily compute that by just summing up the right rows in that big table. Okay, so this is what the joint distribution would actually look like, right? These are the 5 or 6. I'm sorry, let's call it 10 or 12 most highly weighted rows. Okay, so the most common thing combination is the effect of the. Okay, and none of these things are very frequent because of course there are many combinations of 5 English words. Okay. But this is what the distribution looks like, okay? And like I said, it has on the order of 100,000 rows in it that have non-zero weight, okay? So this is the joint distribution. Are there any questions? People sort of understand what I'm talking about? So we talked about this at some length in 601 when I taught it. So if you're taking 601, if you took 601 recently or 701, you've probably seen this before, okay? Just to test to see how well it was, I basically use this to build a context-sensitive spelling corrector. So all I've got is this table, okay? And as a test set, I took something that was like different. I took some data that wasn't novels or textbooks. There are about 700 cases where that one of those 2 words was used, okay? So there's like 723 n-grams. Okay, not all of them were distinct. There were some overlaps. Okay, and now we tried to predict the center word. Okay, so how do you predict the center word? Well, you just look at the 2 words to the left, 2 words to the right. Okay, and you can predict now the probability of the center word C, right? So you can predict the probability of that center word given those things using the joint probability distribution. And the way you do that is you just sum up those things and look at the probability of that sum divided you look at the probability of this thing with some particular value of C divided by the probability of that with summing up all the possible values of C. Okay, so that works okay, but if I give you a particular combination of words, right, maybe like any manner blank the principal. All right, it might be that occurs in this financial news corpus, but never occurred in any of the Google books, right? Or maybe it occurred, but not at least 40 times, so it's not in the n-gram corpus. All right, so if that doesn't work, we'll sort of back off and try an easier model. So I'll just take the 2 words to the left and 1 to the right. If that doesn't work, I'll just take 1 on either side. If that doesn't work, I'll take 1 to the left. And if that doesn't work, I'll just guess essentially effect. All right, so this is my model. It's just using the joint model. Okay, and then sort of this little cascade of tests. Okay, so just to give you an example of how that classifier works, okay, for the classifier, if I give it the combination, the cumulative blank of the, all right, That's in the data set. Okay, it's in the words data set, and it's always effect. Okay, so the probability of effect is 1.0, right? Or go into blank on January, effect, probability 1.0. Okay, but here's one that's a little hard. From cumulative blank of accounting. So sadly, even with 1 million books in English, the topic of accounting seems to be somewhat underrepresented, right, in the literature, of novels and so on and so forth. So there's no instances of this combination of 4 words with anything, with either affect or effect in the middle anywhere in the corpus. Okay, so we get no information, so we have to back off. So we'll sort of ignore this thing and see, well, do I have from cumulative blank of anything, right? Nope, not there. Okay, but cumulative blank of is there, and it's always effect. Okay. All right, and then would not blank finance minister is never there, and you have to back all the way up to blank not, which says it should be affect. So you would guess it would not affect the finance minister. Okay, so this is how the classifier works. Here's how well it does. Okay, so when I actually have something here, remember there's 700 or so test cases, right? So I actually have data for those 4 context words 100 times. And it's almost always right. There's one case that made a wrong prediction. Okay. Here, it's more frequent. Okay, so these are the cases where this one actually applies, and this is sort of the ones where this applied, but the one above it did not. Okay, so these aren't cumulative. And here there are 6 errors. Okay. So as you can see, as you get smaller and smaller contexts, you get higher and higher error rates, which sort of makes sense. All right, eventually you're really not doing very well. Okay, so if I'm allowed to basically look at just the cases where I sort of have a high confidence prediction, say maybe when one of these 3 things works, then I have about a 5% error. Okay, so 95% of the time I'm correct. If I look at just sort of these 2 right here, which is about a third of the time, okay, that's a 3% error. Okay, so if I take all of these guys, that's really almost everything, and it's about a 15% error. All right, so if we look at these numbers here, we're actually getting about a 5% error at the end of the day with this huge training data. So 5% is not too bad, okay, perhaps, right? So it kind of depends on the goal of the system, right? But if what we're trying to do is we're trying to somehow alert the user that when we think he's made a mistake, this kind of might be enough, right? So let's see, that's be 100, 250, 400. So about half the time when we could make a suggestion, we do make a suggestion, and we do make a suggestion. We're right about as good as frequently as sort of these presumably state-of-the-art in 2000 learning methods did. Okay, so just by using a lot of data, we have something that looks like a somewhat reasonable density estimate for this purpose. Okay, so what's the assessment here? So counting goes a long way with big data. So it's certainly the case that there'll sometimes when counting is not enough, right? So if I just want to give the user a hint some of the time, that's okay. If I really had to make predictions on everything, maybe this is like some marketing thing or some trading sort of thing. If I'm missing half the chances to actually place an ad that I can make money from, that could be billions of dollars that I'm leaving on the floor. So I mean, it depends on the scenario, okay? But so even though counting goes a long way, sometimes it might not be enough. Okay. Another thing I want to point out here is, so this is a big data task, right? I started with 80 billion words, okay? And then those 80 billion words got trimmed down to, a quarter terabyte of n-gram data, okay? And then finally that got boiled down to, something like 100,000 rows of numbers. Okay, so more on the order of like 1 megabyte of data. Okay, so what's the summary of that? So sometimes the work is basically taking that big data, figuring out what statistics you want to pull out, what you need to count for your task, and pulling out those statistics. Okay, so here, in some sense, another lesson you could take from out of this is data preparation could go a long way. All right, so I certainly don't want to do a prediction on, in the inner loop of my editor on 80 gigabytes. On 80 billion words of text or a quarter terabyte. I'm not going to run through that every time the user types a new word. Okay, but it would be fine to do something like this. Okay. The other thing is density estimation is actually a very important thing to be able to do. Right? It's important to know not only if you've gotten some question right, but whether what your confidence is. Okay. So count turned out to be a pretty good density estimator, right? If you've got if you've seen something many times in the past, you usually know, how to behave in that context. So counts are actually a surprisingly good density estimator. So I'm not going to say a whole lot more about this in this class, okay? But I would say they don't say this anymore, but probably like 10 years after Google started, the head of research, Peter Nord, would come up in front of talks. And he'd say, well, what do we do in machine learning? We count. We basically just do counts. We're really good at counting lots and lots of things at scale. So we don't do fancy machine learning. We just count. OK, so moving on. So past counting, beyond counting. All right, what's beyond counting? So a density estimator basically is counting occurrences of some particular compound event, right? So you're basically, in general, what you're doing is you're taking your input attributes here. It would be the 5 words before, the 2 words before, 2 words after, and the word in the center, okay, and estimating a probability. So that's the probability of seeing that joint event, those particular values of those inputs. There's some other types of machine learning systems that we use a lot. So a classifier takes those input attributes and predicts some categorical variable. So here the prediction I was making was either affect or effect. Okay, you can also look at regression where you output a real valued output. And there's actually a way of taking a density estimator and turning it into a classifier. And the basic idea is you take your labeled data and you build a density estimator of the labeled data. And then if you want to find out which class value should be plugged in, so in this case, there are only 2, affect or effect, and the 4 other things are the context words. You just plug in each value and see how probable it is. And then if you just want to predict the one that's most likely, you just choose the one that has the highest predicted probability. Okay? So that's a way of turning a density predictor into a classifier. That's basically what I did in this example. Okay? If you want to see a picture of the difference between these two, here's one. So the density estimator is going to look at every joint event. And here an event is just going to be sort of like a position in 2 space. All right? And it's going to predict the probability of that joint event. So here these surfaces are probability. And if I want to figure out what's the most likely class, then so this red mound here is that joint event appearing here with the label red. So really I guess it's 3 dimensions, these 2 spatial dimensions and the class label, right? And the blue mound is the probability of seeing it with the label blue. So we can estimate all these things. And really what we want to do in terms of classification is just figure out what the boundaries are. Okay, when is it most likely to see red? When are we most likely to see blue? In the two class case, right, you can kind of think about a density estimation as sort of measuring the topology of the space of probabilities. And classification is basically just sort of telling you whether you're over or below some threshold. So it's kind of the difference between a topological map of some undersea landscape versus just a map that tells you where the shoreline is. Okay, so there's more information in the density estimator, which is a good thing. Sometimes a bad thing is basically there's more parameters to estimate. But that's basically the difference. So let's now talk for a second about a particular density estimator that we use a lot. You guys have probably seen this before. or maybe you're seeing it right now if you're taking classes concurrently. If we wanted to boost this performance, what could we do? All right, so in particular, if I care about sort of getting high recall, predicting everywhere, what would I do? Okay, so the problem with this estimate is basically there are lots of cases where I haven't seen any particular combination of values. Okay, I never saw, might blank the finance minister in my training data. So an alternative way of estimating a distribution is the following. Okay, so I'm going to call this the naive model. Okay, I'll just build an estimate of each attribute independently from the other ones. So I'll just build a multinomial that tells me how frequently, what's the frequency distribution of each word in the position, 2 spaces before the focus word, or 1 space or 1 before, or 1 space after, or 2 spaces after. So I basically end up with 4 independent distributions that tells me how those words are distributed, and that's all I got. Okay. Oh, I guess 5, 1 for the context word. Okay. So it turns out if what I care about is trying to figure out whether someone, used the wrong word, it's not going to help me. Okay. So why is that true? Well, if I look at like a particular combination, let's say that these are just binary instead of words. Okay. So it makes sense to ask a question like, what's the probability of A being true, B is false, C is true, D is false? Okay. So under the naive model, right, we're assuming they're all independent. So to figure out the probability of that joint event, I just multiply those separate probabilities. Okay. All right. And this is easy to learn. Okay. Right. All I've got to do is basically, count the frequency of each value of each variable. Okay. We could use a maximum likelihood estimator, or we could do some smoothing. But it's a very simple algorithm. And so what would happen if I did it here? So for n-grams, what's the probability of effect given the first word is will? So this might be will not affect blah, blah, blah. Okay? Will not affect finance minister Smith. Okay? So in the joint distribution, okay, this is the probability of effect given A equals will. So this is the distribution where I just have this big table of all the n-grams. Okay, so I add up all the probabilities of all the n-grams that have effect and will, and I divide that by all the n-grams that just have will in the first context position. All right, and it turns out to be 38%. Okay, so roughly 1 time out of 3, something like that. The word you're predicting is effect, given that the word 2 things to the left is will. All right, so in the naive model, okay, it turns out. Well, so this is the probability of effect. If you kind of like write this out, this will be the probability of effect times the probability of will, right? Divided by the probability of will. So you can simplify that just to the estimated probability of effect. All right, so it'll be 0.94. So that's really different. Okay, so that's a very different answer. If I ask what's the probability of effect given the the second context word is no, then in the joint probability, it's almost always effect. Here, it's still 0.94. Okay, so so the problem is that in this model, I've basically said the class variable, the thing I'm trying to predict, is independent from all the context variables. So of course, I can't use the context variables to predict the class variable. It's independent. That's what my model says. So I've got to break that independence assumption a little bit in order to make some useful predictions. But I don't want to break it too much. If I go all the way back to the joint density, then I can make predictions, but I may not have enough data to make predictions in many cases. So what we do is sort of do this partial model. Okay, so instead of estimating using this model here, where we assume everything is independent, okay, what we're going to do is we're going to assume that everything is conditionally independent given y. So we're going to estimate the probability of all the context variables given y, and we'll just estimate that as this product here. Okay. This is equivalent to basically saying the probability of xi given y is basically the probability of xi given all the other input variables in y. Okay. But this is the basic idea. I'm going to introduce independence, so I'm going to assume that these xi's are independent, but only given y. So to estimate this, we can use the same sort of tricks, and we're going to break this down in a second. Okay. So let me step forward a little bit here, okay, before I stop and ask for questions. All right, I'm going to give you an algorithm coming up next, okay? So this is what I'm going to start out by assuming I know what the data looks like. So the data, first I've got the first element on each row. Let's say it's all tab separated. It'll just be some ID for that example so I can help debug, okay? It's not really going to be used by the algorithm in this particular case, but it could be useful. Then I've got these attributes, okay? So we'll have a set of context words here. There are 4 attributes, 1, 2, 3, 4. The 4 context words. And each one takes a discrete value. All right, so here the domain is, a vocabulary of English words, right? So it's a very large set of possible discrete values, but each one is going to take a particular value. And then I've got one special class label, okay? So every example has got the ID, it's got these attributes, and it has a class label. We've got one for training and one for testing. Okay, so I'm going to assume the data set doesn't fit in memory. Okay, so my training data is, for example, the Google Ngram data or something. I'm not going to try and load it all into memory, but I am going to assume I can store the model in memory. So the model being basically these conditional probabilities, the probability of x given y. Okay, all right. So since I can't fit the data in memory, what I'm going to do is I'm going to stream through it. Okay, so I'm going to go example by example. I'll look at each example in turn. I'll update some sufficient statistics for my classifier, then I'll throw that example away. Okay, so here's sort of our first version of a naive Bayes classifier. All right, so I'm going to stream through the training data, okay, and I'm going to keep all the statistics in a hash table. So I assume this hash table is going to fit in memory. Okay, next week we'll talk about what happens if it doesn't fit in memory. But for now, let's keep it simple. Let's say it fits in memory. Okay, so basically, there are a couple of things I want to keep track of. I want to keep track of the probability of these joint events, okay? So I want to keep track of the number of times these joint events occur, okay? So the joint event is some particular value of the label, x, y, and then some particular value of one of the context variables. So if I see something like, is the effect of weather, for example, right? Then I'll take is an effect, right? Pair them up, and I'll increment that counter. Then I'll take the an effect, increment that counter, and so on and so forth. Okay, so that's what I do, and then basically a couple of other counters here. So I'll keep track of the number of times a particular event occurs. Actually, I'm noticing there's a typo in here. This should really be, and no, that's okay in this case still. All right, we're good. All right, I take it back. All right, so that's the training phase. We've just incremented our counters for the sufficient statistic. Now in test phase, what I want to do is I want to classify. Okay, so I'm going to go through each example. I've got, let's say this is like I'm doing, I know what the real label is. Of course, we're going to try and predict that, not use that. And I have the context words for that example. All right, I'll go through each possible label I could do, and I'll compute the probability. So I know what the probability is, right? It's going to basically be the product of these conditional probabilities times the probability of seeing that y. Okay, then whichever one scores highest, we'll just return the best one. Okay. So if I want to figure out what this count is, this conditional probability here is just that ratio, okay? And we can estimate that by some ratios of counts, right? So the probability of seeing y equals y prime, let's say. All right, so some particular value, say affect rather than effect, all right, will just be the ratio of the number of times you've seen it versus the number of total examples you've seen. And then here we've got a similar sort of thing. It's the number of times we've seen that particular context word with that value of y divided by the number of times we've seen that y. Okay? So that's the algorithm. Now, one disadvantage of this is you ever see a word in test that you never saw in training, then basically you'll get a 0 for this count here, right? Which means this whole product turns out to be 0, and it'll be 0 for every possible label you have. So what we tend to do is do some sort of smoothing, okay? An easy way of smoothing, and there's pointers on the website to a big discussion of smoothing, or there's discussion in Tom Mitchell's book of the readings in Tom Mitchell's book about a particular type of smoothing. But one thing we can do is we can pick some prior probability for each of these things, and basically imagine that I've n m examples distributed according to that the prior probability. Okay, so I can pick some small number for qx and some small number for qy. So usually qy would be something like, 1/2, okay, or maybe 1 over the number of labels you've got. Qx would be basically, 1 over the number of words you've got. And m would probably be something like 1. It would be some small number, okay. And that actually might also give you problems. So one problem you often get dealing with probabilities is that when you start looking at multiple products of probabilities, the numbers get really, really small, really fast. It's probably okay with 4 context words, but if I went to 8 or 16 context words, then we might have round-off errors, and this might just sort of get approximated as 0. So a better way of doing that is to do this in log space. So instead of looking at products, look at the sum of logs. All right. So this is a pretty reasonable version of naive Bayes. And just to plug it in here, okay, in the context of this affect-effect data, we basically have 4 attributes: first, second, third, fourth context word, and the label is either affect or effect. Okay, so are there questions? How many people have seen naive Bayes before? Okay, how many people don't really want to see it again? Be honest. We're going to get it'll get hard before it gets before we stop. All right, but it's going to get easy. It's going to stay easy for a little bit. So the problem we're going to be looking at in our first homework is text classification. Okay, so a common choice of features could be, we've got n different features. So you could use the words in the document. So the first feature could be the first word, the second one could be the second word, and so on and so forth. All right. So that's a bad choice because the probability of seeing the word hockey, given the label is sports, is probably not that different from the probability of seeing it in the 11th position, given the label is sports. Right. So instead of treating them as different variables, you can sort of treat them as copies of the same variable. All right. So the way to modify this algorithm basically is just throw away this little subscript here, okay, where I'm looking at the counts associated with a particular context variable and kind of merge them all together. So I just have counts for the context variable x. All right. And then again, we can do the same sort of thing. We'll go and look at this in log space with smoothing. All right. This, I believe, yeah, so here there's actually, here's where the bug is, okay? So the bug is here when we're looking to see how often x occurs with y. The thing I want in the denominator is not basically how often the variable y occurs, but how often any word occurs with y, all right? So we look at the conditional probability that I'm estimating the right count would be something like this. So I want to find the number of times that there's any word co-occurring with that label y. So I want to figure out the conditional probability of that word being some specific xj. That basically means that here we have to have another counter where we increment that count here. Okay. So now we have a training document and a test data document. Okay. This is how you could do text classification. Turns out you could also do this for situations where you have distinct context variables. So for the context-sensitive spelling correction, I don't really want to throw everything in one pot. I really want to treat the words to the left as different from the words to the right. The word that's 2 spaces to the left is different from one that's, 1 space to the left. Okay. But what I could do is I could basically distinguish them by putting some little prefix. Okay. So I could basically add to each one of my context words a little string that tells you whether it is in the first, second, third, or fourth context position. Okay. And then I can just run the naive Bayes code sort of exactly the same way. All right. So this will give me this basically provides a way of encoding it provides a way of encoding multiple context variables, without, changing this very simple naive Bayes algorithm. So a question for you to think about. It's not on the quiz, but are there any differences in behavior, okay, between this formulation of the problem, okay, and the formulation I started with, where I have 4 different context variables, all right, and I keep track of their sufficient statistics separately. So you can think about that kind of offline. All right. I'm going to now stop talking about the algorithm and talk a little bit about the complexity. And then I'm going to talk about another algorithm which has sort of similar complexity. So before I go on, questions? Are there any questions? Okay. All right. So how long does it take to run this algorithm? Okay. So this is what the algorithm is. All right. So I'm going to assume that everything fits in memory. Okay. So that means that adding things to the hash table is a cheap operation. It's a constant time operation. If my data set, my training data set, has n tokens, right? So that means n words in the training set, okay? Then basically, I can focus on this inner loop right here, okay? Every time there's a token, I've got to increment a counter, or maybe 2 counters if I'm doing this one, all right? So every token in the training set basically corresponds to 1 hash table update. So it's order n, it's linear time, okay? And what I'm doing here is sequential read. So that's the operation I'm counting, right? I'm doing, n sequential reads through the data set, or reading, n bytes of the data set, okay? Then in testing, I've got, pretty much the same thing. I'm reading that example n, all right? This operation here is linear time in the number of words in the document, all right? The only thing that's a little bit different is now I basically have to do it for each label, right? So if I have 2 labels, it's twice as long. If I was trying to do classification into 1,000 different categories, right? This inner loop here where I'm going over each category has to happen 1,000 times, all right? But it's still sort of a reasonable thing. So the complexity is basically the number of labels times n prime, where n prime is the number of bytes in the test set, okay? The process, again, is basically just count the events in the training data set. Presumably, in sort of a real setting, what we're doing is we're building a classifier that's going to be used somewhere else. So we want to think about that and model that. So the other thing we have to do is write the counts out to disk, right? So there are a couple of ways we can bound that. So certainly the number of counters I get is not bigger than the size of the test data set, the training data set, because I only increment a counter when I see a word. Okay. So certainly it's not larger than n. okay? It's also the case that every counter is some word in the vocabulary paired with a label, okay? So if the vocabulary is small, then we can bound it by the number of things in the vocabulary times the number of labels, right? So every event is a cross product of those two things. So it's also not bigger than that. So that's an upper bound on how big the classifier can be. And of course, that's how much memory I need, okay? A good bound, if we're assuming there are not too many labels, that's sort of a constant, then it's just basically the size of the vocabulary, okay? The vocabulary is just all the words that appear. Okay, so when I classify the test data set, I'm going to assume I do two things. One is read off the old classifier, and the other thing is scan through the test data set. So this is going to take time order v plus n prime. Okay, so notice I don't know necessarily that n prime is bigger than v, right? Okay, it could be the test data set's pretty small, and the vocabulary is really big. And then again, the worst case memory usage is basically, again, the size of the model, the size of the number of counters I've got. So that would be an estimate of the amount of memory I'm going to need. Okay. Okay, so this is an example of a streaming learning algorithm. So this is not a formally defined term, but what we generally mean is every example gets read once. Okay, so you go through the input data, the training data once. All right, you go through it in order, sequential order. Usually you can go through it, ideally you can go through it in any order you want. Okay, at any point you could start doing classification if you want to, right? So you have a classifier that gets updated incrementally at every point. So here are sufficient statistics for naive Bayes, our classifier. Okay, so that's also the case here. Okay, so in a streaming classifier, ideally you don't use a lot of memory, right? So if I was loading all my classifiers into memory, and at the end of the day classifying by saying, well, I'm going to use the label of the thing that's closest in training, k nearest neighbor type algorithm, that would be cheating. That would not be a streaming classifier. Okay, so the memory requirements should be small. Okay. Usually, we'll assume it's like not more than like the square root of the size of the data, because it turns out to be a convenient assumption usually that a computer's RAM memory is about square root of its disk memory. Ideally, the order doesn't matter. Okay, so in real life, of course, we may not be able to control the order of the examples, and changing the order of examples if you have a billion examples will take a little bit of time. Okay, so if you have to sort them or even randomly reorder them, that could be an expensive operation. This is actually a really hard property to get a learning system to have. Naive Bayes is unusual in that it doesn't, order doesn't matter. Okay, so naive Bayes is sort of like the ultimate streaming learning algorithm. It satisfies all these things very nicely. I'm going to talk now in the last 20 minutes, half hour of class, about another streaming algorithm which you may not know about. Okay, this is an algorithm that came out of the IR literature called Rokus Algorithm. It's nearly as old as naive Bayes. It dates back to the 60s. It's a very simple algorithm. And it's like naive Bayes. There's only one pass through the data. Order doesn't matter. This is the write-up I'm kind of using in this description, but like I said, it's lots of other ones. So there's a bit more math here, and the math is a little bit different. It's not a probability-looking sort of math. We're basically just using a lot of vector expressions. Okay, so here's some notation. So DF stands for document frequency, right? So this is the number of times, the number of different documents a word appears in. Not the number of times the word appears in the corpus, the number of different documents, distinct documents it appears in. All right, so this algorithm came out of the information retrieval world. All right, and TF of W and D is the number of different times the word appears in the document. Okay, so it's a count of how many times the word appears in the document. All right, so I'm going to look at a couple of measures. So the inverse document frequency is basically the document frequency, traditionally divided, and it's 1 over that, traditionally multiplied by the number of documents. So this is basically the fraction of documents that have that word. Okay, so an interesting fact is if you look at frequent words in English and many other languages, they're not really all that important for topical classification tasks and retrieval class tasks. So if I ask you, if I use the as a feature for naive Bayes, it's probably not all that helpful, just because the appears so often in so many different documents. So words that have a higher IDF are more likely to be content words. Okay. All right, now I'm going to do a little bit of scaling. So this U measure here is basically scaling as follows. So I'm going to look at the log of the term frequency and multiply that by the log of IDF. Okay, why that formula? Empirically, it sort of seems to work. And we're actually going to add 1 here. Okay, so anyone want to venture a guess as to why I want to add 1? Yeah, that's right. Yeah, if you take the log of 0, your head explodes or something, right? You just don't want to do that. But if a term frequency is 0, so it's a word that doesn't appear in the document, all right, then the term frequency plus 1 is 1, right? And the log of 1 is 0. Okay, so this whole thing turns out to 0. So this basically has 0 weights for all the words that are not in the document and only has non-zero weights for the words in the document. All right, so U of D, the boldface here means it's a vector. Okay, so that's just a vector where every component is this measure, this function for that word. So each word corresponds to a component of the vector. If I've got 10,000 words, I've got a vector with 10,000 components. All right, it's going to be a really long vector, no matter how long the document is. Right, the vector is always going to have 10,000 components. But if the document only has 100 words, then I can guarantee that all but 100 of those components are going to be 0. So it's a long, sparse vector, and there are tricks for storing that efficiently. So that's a vector that I'm going to use to represent a document. All right. Now, from that, I'm going to construct a vector for each class. Okay. So what's the vector for each class? Well, I'm going to basically take all the documents that are in that class. All right. And I'll sum up their U vectors. Actually, I'll sum up their U vectors, and I'll divide that by a scalar quantity, which is just the Euclidean norm of that U vector. So this quantity here is, I wrote it here actually, in case you've forgotten, right? It's basically the square root of the sum of all those things. So we'll look at each of those things. We'll sum them up. Well, actually, we'll average them, okay? Because we're looking at 1 over this, okay? And we're going to do the same thing for all the things in the complement of y, okay? So all the things that don't have the label y. So we'll average those all out, all right? And we weight these. So there are a couple of traditional weights for this. A pretty reasonable weight to use is to let this be 1 and to let that be 0. So in other words, you're just averaging the positive examples, okay? And now when I want to classify, I do something that looks like a nearest neighbor, okay? Except I'm doing a nearest neighbor for these class vectors. So I basically want to find out which class vector is this document closest to. And when I say closest to, I want to use this measure right here, okay? So I take this document vector and I normalize it. I take that class vector, I normalize it, right? And then I just look at their inner product, okay? This is cosine distance, because this is also the formula for the cosine of the angle between the U vector, the U of D vector, and the U of Y vector. Okay, so that's Rokus algorithm. Okay, very simple. Okay, there are lots of variants for this U function. This is one that a lot of people use. But there are other ones that people like. One thing that is always true is that the U value, the weighted value for that word, has got to be 0 for the words that aren't in the document, because otherwise this vector gets large and hard to represent. So when we're storing that, there are a number of concise ways of storing it. We have a question. Yes.
Sorry, what's the CY stands for? The CY.
CY is the set of all CY is the set of all documents that have label Y. Anyone get that? CY is a set of documents that have label Y. So this iteration here is over the positive examples. This is 1 over the number of positive examples. So we're averaging the positive examples. Okay. So one easy way of storing this data would be, again, with a hash table. So we just store the non-zero values, right? So for each WI that occurs in the document, we'll store this number U of WD. So then the hash table, will explicitly not store the 0 values. I should say when I'm talking about hash tables here, I'm assuming that you've done, here and here. I'm assuming you've done a little bit of work. So, if you ask this counter hash table, how many times this event occurred, and the answer is 0, so the hash table's never seen it. It's not a key in the hash table. Then you would return 0. So that has to be wrapped a little bit. Okay. Okay. So this tends to be a small object, right? The size is the number of distinct words in the document D. This tends to be a big document, okay? Because if I've got many positive examples, right, I'll probably have many non-zero values after I do that averaging, right? In fact, a pretty good estimate of the number of values I'll have will be the vocabulary size. Probably if for a big data situation, it'll be sort of about the number of words that appear in the vocabulary, all right? So UI is going to be much larger, even if I tried to store it compactly with a hash table or something. There's just not going to be that many zeros. Okay, so that's the Rokus algorithm. It works pretty well. There's a paper now from, I guess, almost 20 years ago that looked at basically 2 estimates of TF-IDF and sort of the kind of naive Bayes that I just described, multinomial naive Bayes, on a bunch of kind of sample problems, and it worked pretty well. This is Rokus algorithm, and this is like sort of a slight variation of that. It's still the same algorithm, it's just a different weighting scheme. Question?
In case of a streaming algorithm, how do we define the vocabulary size?
How do you define the vocabulary size in a streaming algorithm? So one question is, do you need to know the vocabulary size of the streaming algorithm? Okay. So which of these things do we need to know the vocabulary size? So for naive Bayes, we do at the smoothing stage. Okay. So yeah, I did a slight simplification here. If you're going to use the particular smoothing algorithm that I talked about, which uses the vocabulary size as priors, you have to keep track of that, or get that number somewhere else. For this algorithm, you don't need to know the vocabulary size. You do need to know the number of documents, right? So yeah, it's not unusual. You'll have like sort of a few kind of extra kind of high-level counters in addition to, you could kind of keep track of those numbers as well without much overhead in this, without any kind of additional kind of order-wise overhead in these algorithms. Question?
What's the intuition behind UI? So why do we have UI like this equation?
Well, the best intuition, I guess, is a geometric intuition. So if I've got a cluster of points over here and I've got a cluster of points over here, okay, so over here is class 1, over here is class 2, okay? So what this is basically doing is it's averaging out each class. So it's the centroid of those classes. So you compute the centroids of those classes, and at classification time, you try and figure out which centroid it's closest to. So that's a geometric intuition, okay? Yes?
So even in this case, since we are summing over all the documents that belong to class Y,
Yes.
right? So for that, the U vectors need to be of the same length for each document then, right?
Yeah.
Or we just assume rest is 0 for the document.
So the U vectors have to be the same length. If you were, it depends on what data structure you use for storing the vectors, okay? So one way of thinking about this is basically when you work with those vectors, you're just padding it out with zeros at the end for any new vocabulary items you didn't see, okay? But if what you're doing is storing only the non-zero counts of each document, okay? Those set of non-zero counts don't change, okay? And when it's time to normalize this doesn't involve the size of the vocabulary, right? It's a sum of the squares of all the weights in that hash table, basically. So this formula doesn't use the number of items in the vocabulary. Okay, the only thing you're going to use is the number of documents. Okay, my analysis, when I said big O of blah, 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 then I used the size of the vocabulary. That's just math, so we can sort of figure out if my algorithm is faster than your algorithm or vice versa, right? When we're implementing it, we don't need that quantity. Other questions? I'm glad you guys are asking questions. Sometimes with a crowd this big, nobody wants to ask questions. It gets really boring standing up here and just talking and talking. Okay, this is another giant survey of a whole bunch of different text classification algorithms that people use. So this is naive Bayes right here and a couple of different benchmarks. This is the Rokus algorithm right here. This is Eta Boost, which is sort of, I guess sort of a much more expensive algorithm. So I don't know if I've got these blown up. This may be a little bit hard to see. But basically kind of the short story is that the Rokus algorithm is extremely competitive with that naive Bayes algorithm. Okay. This is another analysis that people did. So this is using boosting, which is a wide margin classifier. Okay, and they were comparing it to Rokus. Okay, so the boosting guys were Rob Shapiro, who was one of the two kind of inventors of adaptive boost. He was the guy who invented boosting and adaptive boosting. And Yoram Singer, who went on to become a very famous guy. And then Rokus, the implementation of Rokus was done by Amit Singhal. Amit went to Google in, I'm going to say 2001, 2002, and he was sort of the head of search for a long, long time. Now he's like a vice president. But these guys really knew what they were doing, and they were basically sort of competing to see who could do the best. So for this benchmark case, this is the error of Rokus minus the error of Eta Boost, okay? And it's plotted against the number of positive examples. And this is the same thing with sort of a slightly different measure of quality. So just look at this one on the left here, which is the error rate. So you can see on average Eta Boost did better, but there's a lot of variation. There are lots of cases where there is very little difference. And really the only cases where Eta Boost was able to improve was cases where you had more positive examples. Okay, so Rokus, and this kind of makes sense given where it came from, was basically used as sort of relevance feedback. Rokus is great when you have a relatively small number of examples. Okay, so this whole description of Rokus is kind of here for two reasons. One is, so the streaming algorithms part doesn't seem to be just about naive Bayes, sort of puts it in a slightly broader context. The other reason is because, part of what I'm also trying to do here is give people a sense of what practically works and what doesn't work. All right, so we don't always know why things work, but after many years, we often know what sort of things do work. Okay, these aren't always the same. Okay, so here are some useful tricks. So I talked about doing a brute force estimation of the joint distribution. If you've got a lot of data, particularly if you're only having to make predictions some of the time, that's an incredibly useful technique. So if you're looking at something if you're looking at a new problem, the first question to ask is, well, what if I just counted, right? What if I just count and divide? How far does that take me? So naive Bayes is very useful, okay? So we're going to talk coming up on two things called stream and sort and request and answer, which are basically techniques for dealing with basically increasing the range of things I can do with streaming algorithms. We're going to talk about this later on. So TF-IDF weighting, particularly this inverse document frequency trick, is actually useful in a lot of different settings. It's often useful even when we don't know why it's useful. So just to give another example, around 2003, there was a paper which has been, I want to say, not ignored. A lot of people have implemented it. No one's done sort of theoretical analysis that I know of to explain why it works. But they looked at something that he called TWC naive Bayes. All right, so it's a variant of naive Bayes and compared it to SVM. All right, and really basically sort of tied SVM, right? And it was almost as fast as naive Bayes. It's still a streaming algorithm. All right. So what's the basic idea behind this algorithm? Okay, so here's the whole thing. Okay, so you start out, and what you basically do is a TF-IDF transform on the data. Okay, right? Then you actually learn the class for the complement of each class. You learn a naive Bayes model for the complement of each class. So the negative examples of each class instead of the positive examples. All right. Then there are a couple of other tricks. Okay. All right. But essentially, what you're doing here is you're first doing a TF-IDF Rokio style weighting of all the counts. Then you're running naive Bayes, pretending that each word, instead of appearing, let's say 3 times in the document, you're pretending it appears, 4.7 times in the document, or 4.7 is its TF-IDF weight. All right. So why would that help to do? Why would you on Earth would you do that? I mean, naive Bayes sort of has this clear generative model, right? There's a story behind it we can tell. I have no idea what that means. Okay, right? It's a computation you can do. I have no idea why it means, but it turns out that actually that helps a lot. Okay, in the experiments that were done with SVM, it's also very common to do a TF-IDF transform of data on SVM before you run that. So this is, again, sort of emphasizing, the generality of this trick. This is something that sort of seems to work well in a lot of different contexts. All right, so I'm going to stop here rather than jump into the next topic. So you guys get early dismissal by like 7 minutes today. I'll stick around if there are questions.